Okay, now we can start talking about Voronoi diagrams. Voronoi diagrams have been studied in many different, by many different scientists in different areas, by astrophysicists in 17th century. I mean, if you take notes and comments at the end of the Voronoi diagrams chapter, you are going to see that in the last century, in 1960s, for example, Voronoi diagrams have been rediscovered by biologists, physicists. So when biologists, and what they do is their main purpose is to partition the plane into regions which show the influence of certain sites around them. So the problem definition is this. We are given a set of points again. We are going to be dealing with, our input is going to be a set of points in 2D plane. We can call these points also sites. Okay, so these are sites. And here what we wonder is that given a point on this, in this plane, another point, which is the closest site to this point? And what about this one? So we are given a point in this plane, we want to find out the closest site to this point. For example, you may go to a city and you may be wondering the nearest post office. So these sites may correspond to post offices, and you may want to go to the nearest post office. In that regard, the problem does not seem to be difficult. I mean, just if you have even in a GPS systems, for example, if you know your location, by computing your distance to every one of these sites, you can find the closest one. So it's again a trivial problem. But here, if you want to see, ask different questions. For example, if you are going to open a new post office, a new site somewhere, which other sites this site will be in competition with? Or this may be a restaurant, for example. And so if we ask the question in that manner, from the query point of view, it was given a query point, we were wondering which was the closest site. Now the problem turns into certain regions. For example, given a site like this, what are the set of points which are closest to this site? So we are going to be talking about influence regions, I mean certain regions around these sites. And these regions are going to contain points which are closest to that site. But are the regions going to look like this? No. So the region, I mean the subdivision of the plane into these regions is called the Voronoi diagram. For example, let's now discuss how this, for example, a point here, I mean, if you draw something like this, it's not a Voronoi diagram because a region here, a point here is not assigned to anybody. But by definition of the problem, any point in the plane has some closest site, right? So it has to be complete subdivision. There shouldn't be any points left out. So any point in this, and it may be possibly unbounded, because for any point, this region here, for example, may be closer to this one. So all the points are going to belong to this site. So when we talk about it, so some parts of this planar subdivision may be unbounded. Let's think about the easiest case. What happens if we have only two sites? Okay. Saying now, what are the influence regions, or what are the dominating regions of each site, site 1 and site 2? For example, which points are closer to site 2? Which points are closer to site 1? How are we going to give a subdivision in this case? Yeah, the bisector of this. So this is the bisector of the line segment between these two sides. So this full line, which extends to infinity in both directions, is going to, any point to the right of this line is going to be the region of this side, and this part, this half plane, is going to be the region of this side. And what happens if we have collinear? If all the points are collinear, we are going to have these bisectors in between them like this. Now the question is, what if I have a point here? What will happen now? Now it's not, for example, here a certain region is going to be, and this is, what will happen is that there will be no full line left, okay? Because even here, even this full line is going to be intersected by the, I mean, there will be some points above here at this region which are closer to this one. So all these full lines are going to be disrupted. But what we can do is that if we analyze this problem more, we see that each of these pairs of sides, they can be identified by two half planes. And when we talk about the region for a specific side, this region for a specific side is indicated by Voronoi. It's called, a term for that is Voronoi cell. Okay, it's the Voronoi cell of that side, and that Voronoi cell can actually be computed by intersecting all the half planes that belong to this cell. For example, here let me show a set of points in general position. Okay, imagine these are the 1, 2, 3, 5 points, and I want to find out the Voronoi cell of this point. 1, 2, 3, 4, 5. Let me indicate the half plane that by comparing these two, let me use the terminology in the book, and let's name these bisectors as well. Okay, the half plane, so this is the definition given 2 points. This half plane is determined by the bisector of these 2 points, the line segment. Okay, this is the line segment between Pi and Pj. The bisector of this line segment is this line, and this half plane indicates the plane which is closer to Pi. So these are 2 different half planes. Pj, Pi is the one that belongs, it's the part that belongs to J, and this is the half plane that belongs to I. Now, for a given site like this, 4, what I will do is, if I compare it with 1, if I pairwise compare this site 4 with all the other remaining sites, I'm going to get, for example, I'm going to look at this. I'm going to look at H41 first, which is going to be this region. And I'm going to look at H42, which is going to be this region. H43 and H45. So all these half planes are going to indicate, comparing with all the other points, they are going to give me half planes that belong to site 4. And the intersection of these half planes is going to give me the region that uniquely belongs to this site. Okay, so we can say that the Voronoi cell of site 4 is going to be a convex region. Okay, because it's going to be the intersection of half planes, and we have seen the intersection of half planes in the linear programming and the casting. In the mold problem, we also did the intersection of half planes, and we have seen a solution that does it in n log n time. In n log n time, we can find the intersection of half planes. So we can find the Voronoi cell of this site 4 in n log n time. And if we do it for all the sites separately, in n square log n time, I can compute the Voronoi diagram actually. Okay, if you find the Voronoi cell of each site by intersecting its half planes separate for that site, by intersecting these half planes, we find the Voronoi cell of 4. By intersecting the half planes of this site, I'm going to find the Voronoi cell of 3. And at the end, in n square log n time, I can actually compute the Voronoi diagram. Today, we are going to see another algorithm, which is going to reduce this complexity to n log n. And by using a plane sweep algorithm, we'll be able to compute the Voronoi diagram of n points in n log n time. But now let's look at some properties of Voronoi diagrams. First, now what we know is that each Voronoi cell for a site is a convex region, but possibly unbounded, since the intersection of half planes may be unbounded, the intersecting region. So some Voronoi cells for points at the boundaries are actually going to be unbounded regions. And again, we can do the same trick to bound them. We can just put a large rectangle over these points that encapsulate these points, which is going to bound the Voronoi diagram. In the book, there are a couple of observations and lemmas. For example, one lemma is that unless all the points are collinear, even if there is one non-collinear point, our Voronoi diagram is going to consist of either line segments or rays or half lines. Okay, there is not going to be full line or curved segment. The Voronoi diagram is going to be composed of edges, which are line segments or half lines. Its edges are line segments or half lines. And another observation about Voronoi diagrams is that what is the complexity of the Voronoi diagram? Is it how many faces? Actually, the number of faces of Voronoi diagram is already given. What is the number of faces? The number of sites. Each site is going to be, if you think about a Voronoi diagram, a subdivision of the plane. For each site, we have a face. So if we have n sites, n points, we are going to have a Voronoi diagram with n faces. But what about the number of vertices and number of edges? For example, is it possible that a single face, a Voronoi face, have n-1 vertices? And if it is so, if it has n-1 vertices, if each face can have n-1 vertices, at the end maybe I have n square vertices. So what is the complexity of Voronoi diagram? This half plane intersection, I have n minus half planes. If all of them intersect with all the other half planes, I'm going to have n square half planes. So is it possible? So let's first think about the complexity of Voronoi diagram. How many? I know that it contains n faces, but what about the vertices and edges? How many vertices and edges can a Voronoi diagram can have? Now, can you give me an example in which a Voronoi diagram, can a face have n-1 edges, for example? Can a Voronoi cell have n-1 edges or n-1 vertices? here's the example from the book. If I have this center side, and if all the other sides around it are arranged in some circle around this side, what will happen is that the Voronoi cell of this may be composed of, actually I have to put them closer, so they have equal distance, so it's there. This is like the center of the circle. These are all bisectors here, and each so it's going to have 1, 2. So this is the end point. This is the one side 3, and this is n minus 1. So, and the Voronoi cell looks like the other. So 2 is here, for example. 3 is here. So it's going to look something like this. Okay, I can have a Voronoi diagram in which one side has n minus 1, this face have n minus 1 vertices and n minus 1 edges. So the question is, okay, this is an example, and I can arbitrarily, if you increase the number n, I can put them in equal in the circle, and I can have a face guaranteed to be in n minus 1 edges. But can this happen for all the faces, or even half of the faces? If you can do it for half of the faces, you are still going to have a quadratic complexity of the Voronoi diagram. So can a Voronoi diagram have quadratic complexity? And the answer is no. By using the Euler's formula states a planar subdivision. There's in a planar subdivision, the Euler's formula relates the number of vertices, edges, and faces. And what it says is that number of vertices minus number of edges plus number of faces is equal to 2. So it's a remarkable formula actually which relates these two. If it's connected, first of all we need to also prove that a Voronoi diagram is a connected subdivision. In other words, there is no region in between which doesn't belong to anybody. And by contradiction actually you can prove that it is connected. So each region is the faces of this Voronoi diagram can be visited, all of them can be visited by going through the neighboring faces or neighboring edges. So it's a connected graph. So it's a planar subdivision. So here, let me do it. So by using this formula, we already know that this number of faces, so given n sides, how many edges and how many vertices can this Voronoi subdivision have? We are going to discuss this. We know that number of faces is equal to n. Okay? And another thing here that we are going to use is that each edge here, any edge in this Voronoi diagram has 2 vertices, right? I mean, these vertices may be shared, but any edge has 2 vertices. Exactly 2 vertices, okay? So we sum the degrees of all vertices, okay? So if you look at, if you know the number of vertices, and if you just check how many edges this vertex is incident to, okay? If you sum the degrees of all vertices, what we do is we get twice the number of edges, okay? So, and another important property that we are going to use, any vertex in a Voronoi diagram has degree at least 3. Okay, we cannot have a vertex, okay, like this. There's no vertex like this because each of these half lines, the reason that there's a vertex in this Voronoi diagram is that there's another side that is another half line, the half plane that intersect at this point. Otherwise, this would be a single half line, which is, there will be no vertex here. So each vertex is incident to at least 3 edges. So this gives us 2 times the number of edges is greater than 3 times the number of vertices plus 1. And this plus 1 actually comes from the fact that in order to make this graph a planar, in order to apply Euler's formula, Euler's formula does not apply to faces which have unbounded faces. So everything should be bounded. So what they do, the trick in the book is to put an edge, to put a vertex at infinity, name it vertex infinity, and connect all these faces that are unbounded are closed with the help of this vertex at infinity. So the number of vertices is therefore increased by 1 to make it a bounded planar graph. And at the end, if we solve by using this equation, if we relate these in this equation, at the end, what we find is that, and if you do here, number of edges is greater than this. Okay, if number of edges is greater than this, if I replace this number of edges with something smaller, okay, since number of edges is greater than this, if I put this here into this equation, I'm subtracting something, I will be subtracting something which is smaller. So this is going to be greater than or equal to 2. Okay, in other words, if you do this, number of vertices minus 3 over 2 number of vertices plus 1 plus n is greater than 2. So this is what we get. And this is going to be minus 1 over 2 number of vertices minus 1 over 2 plus n greater than or equal to 2. So it's going to be minus 1 over 2 nv plus n 3 over 2. And if I put it over there, 3 over 2 plus 1 over 2 nv is less than or equal to n. So I just reversed the equation. So it's going to be, right? Yes, I think I'm doing it right. So at the end, no, it's going to be 5 over 2, right? It's 5 over 2, sorry. So 2 plus 1 over 2. 2 plus 1 over 2 is going to be 5 over 2. And then this is going to turn out to be number of vertices is less than or equal to 2n minus 5. Okay? So it says that the number of vertices are linear. It cannot be quadratic. The number of vertices is bounded by 2n minus 1. And this is the maximum it can get. It can be smaller, but this is a bound by making use of the fact that each vertex has at least 3 edges. Its degree is at least 3. Okay, so this is how we've bound the number of vertices. We can use the same thing to bound the number of edges. The number of edges turn out to be bounded by 3n minus 6, so it's also linear. Oh yeah, you're right. No. This is we have here m plus 1 as well. Sorry. This is number of vertices m plus 1. Okay? I forgot a plus 1 here. So it is yeah, minus 3 over 2 plus 1. Then after that it becomes 1 over 2. Okay? So there's this number of faces is m plus 1. Okay, now I think these are all the things. Yeah, there's another thing I need to define here. It's we are going to use it in computing the Voronoi diagrams as well. Now, if this is the case, if the number of vertices and number of edges are bounded by linear these linear bounds, then we need to discuss about what makes a vertex and what makes an edge, because there are n square possible edges. If you consider the bisectors, okay, there are n square bisectors between all pairs of sides. There are n square infinite lines that you can draw between all pairs. And it means that if, since not all of them, since the number of edges is bounded by a linear number, 3n minus 6, it means that not all these bisectors appear as edges, right? Some of these bisectors do not even appear, and this is intuitive actually. For example, there's a point here, there are other points here. Consider this point here. The bisector between this point and this point is going to lie here, and this is never going to be an edge of this Voronoi diagram, because there are these other sides, the closer sides, are going to define the edge here. This bisector here between this one and this one is never going to appear as an edge in the Voronoi diagram. So that's the main intuition. That's why the number of edges is not quadratic. Some bisectors are not going to appear as edges, and also some vertices, some intersections. For example, the intersection of this bisector with another bisector, this point here, is not going to also be a vertex in our Voronoi diagram. So we are not going to have n square vertices and n square edges. So what are the vertices and edges of this diagram? What are some properties? If we have an edge in a Voronoi diagram, is there a property of it? Is there a certain property that this edge satisfies? Or if we have a vertex of the Voronoi diagram, is there a property that it satisfies? Now, yes, and there are some observations about the edges and vertices. And first, we need to define the largest empty circle of Q with respect to P. So this, it's identified as CQ, I guess. Let me use the same terminology. Okay, given a set of points P, okay, these are our sides, and given an arbitrary point which is not a site, okay, this is now given another point Q which is not a site. So our sites are given in this point set P, and given another point Q. The CPQ is defined as the largest circle centered at Q which does not contain any point from P inside it. Okay, so obviously as you enlarge it, it's going to have some of the points on its boundary, right? If this larger circle, you can prove that this largest circle is going to have some of these sites on its boundary. If not, you can enlarge it more until you touch it, because by the definition of this, the largest circle that doesn't contain a site inside it. It can have it on its boundary, but as soon as we touch some sites, we are going to stop expanding it. But if you touch here, then you can expand it. Now, yeah, it may touch a single site as well. So let's discuss it. If it touches a single site, we may not continue expanding this because since it's the center, this circle is uniquely defined when it touches it, we cannot expand it more. So sometimes one site may be on the boundary of this circle, but sometimes more than one site may be on the boundary. And here are the observations about the vertices and edges of a Voronoi diagram. So here is this. A point Q like this is a vertex of the Voronoi diagram if on the boundary of its largest circle we have 3 or more sites. Okay, so if there are more than 3 sites, it means that it's I mean there may be 4 points on the same circle, but 3 points define a unique circle, and if this circle contains 3 of these sites, then Q will appear as a vertex of the Voronoi diagram. So why is that? So it's again, the proof of it is intuitive actually. If 3 sites are on the boundary of this circle, what does it mean? It means that Q is equidistant to all these 3 sites, right? So if we had 2 sites, these are the equidistant points that are equidistant points to these sites. Now, when there's another site here, we can identify a unique point on this line that is going to be equidistant to these. So it's going to be, therefore, this unique point, which is equidistant to all these 3, are going to define a vertex of the Voronoi diagram. It has to be a vertex because there are no other sites around it. There are no other sites which is going to destroy this vertex Q. And so this is the property of vertices. So a vertex, if you look at the largest empty circle of this vertex with respect to this point set, we see that it has at least 3 sites on its boundary. And the edges are like this. The bisector between 2 sites defines an edge of the Voronoi diagram if and only if there is a point Q on the bisector such that the largest empty circle of that Q contains both of these sites, Pi and Pj, but no other sites on the no other sites either on its boundary or inside. I mean, it cannot be there cannot be site inside because of the definition of the largest empty circle, but there are no other sites other than these 2. So it's like this. So imagine there are 2 sites. Let me also erase this. Pi and Pj here. And this is the bisector of these 2 sites. Imagine this is the bisector of these 2 sites. In order this bisector define an edge or part of this bisector, in order for this part of this bisector to be an edge of the Voronoi diagram, there must be a point Q on this bisector, okay, in which the largest empty circle, I mean this is not, let's have Q here, it says to be at the center of this circle. The largest empty circle that contains this, of this point Q contains Pi and Pj, on its boundary, but no other sides on the boundary. So if there were other points here in between Pi and Pj, we would never find such a point Q, which contains Pi and Pj on its boundary. So such a bisector will never appear as an edge on the Voronoi diagram. So in order to be an edge, it has to be, this edge is going to contain equidistant points to Pi and Pj, and those equidistant points should not be closer to any other site. So these equidistant points, imagine in a Voronoi diagram, if we have a Voronoi diagram, for example, this along the edge, the points along the edge are shared between, this is an edge, is shared between two faces, right? And these two faces were side. It means that all the points along the edges are equidistant to Pi and Pj. And since an edge can only be shared by two faces, okay, you cannot put a third face that share the same edge. So there cannot be another side that is equidistant. So there has to be these points which are equidistant. So there has to be a point Q here, which is equidistant to both Pi and Pj, and no third side. Okay, so only that in that manner we can have this part of this bisector as an edge of the Voronoi diagram. Now, so after talking about these properties, I'm going to talk about the algorithm, computing the Voronoi diagram. If you prefer, we can have a short break, like 5 minutes. Okay, so let's have a 5 minutes break. So do not extend it to 15 minutes, okay? So at most 10. So let's be here at